Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss matrix formulation of geometrical optics. Means translation matrix, refraction matrix, and the combination of translation matrix and refraction matrix, which is known as system matrix, and an idea towards the system matrix in case of thin lens and thick lens. Let's begin. Let me consider a thick lens that bounded by two surfaces that is surface 1, surface 2. X dash is the optical axis let the refractive index of material of lens is mu. Let the refractive index of the medium in which the object is placed, let mu I, and refractive index of the medium in which image is formed, let mu O. This is for input section, that is for output section. Let a point object is here P, the point object, incident ray at first surface Q, after refraction through that of medium S, then that ray refracted as T. That is the point object. That point object at a height of yi, that image, point image, let at the height of y o. This for input plane section, that is for output plane section is P dash, T dash. Parallel to that of optical axis, it makes an angle beta I. Here beta I, that angle is same as this angle. Let that angle be beta 1, that angle let beta 2, that angle let beta naught, beta 0. Here the height for that medium let y1, and for inside that of optical system let y2. So the height, that point Q, for medium having refractive index mu y and medium having refractive index mu, as y1 is equal to y2. Similarly here the height will be y3 is equal to y4. y3 inside that of optical system, here the point Q dash, S dash, that is for optical system. that angle is beta 0. Now the coordinates of the points like P, Q, S and T, coordinates of points P having coordinates distance yi, the angle subtend beta I. So the coordinate of P in the form of yi beta I. Similarly, the coordinates of the point Q angle subtend here beta 1 and the height y2. So y2 beta 1 coordinate of the point S y3 angle beta 2 y3 beta 2 and for the point T y0 beta 0 and for the point T that is y0 beta 0. These are the coordinates of these points. Now look here, the ray in going from the input plane to the output plane, under various steps. Here in PQ the medium is same, so here translation occurs, and at point P due to the change in medium here the phenomenon of refraction occurred, and inside that of optical system there will be no change in medium, therefore here translation occurs, and at that surface again refraction occurred, and like this. So the ray undergoes following processes. Process number 1, first translation from P to Q. From P to Q translation occurred, that is the output one due to the input. So we represent it in the form of matrix as yi beta I, yi beta I, that is a column matrix, 2 rows 1 column, is equal to y1 beta I. That is multiplied to a matrix, that is matrix T M1, which is known as translation matrix. The TM1 is known as the translation matrix. Translation matrix. This is the first translation matrix referred as 1. Translation matrix. The output we get due to this input. This one is the a translation matrix, and that matrix is a 2 cross 2 matrix, as that one is 2 cross 1 matrix, this one is 2 cross 1 matrix, therefore the translation matrix must be 2 cross 2 matrix. Next, this is the first refraction at point Q. Next process, first refraction at point Q. Similarly, at point Q the input matrix y2 beta 1, this section y2 beta 1, then the input of y1 beta I, this is the output we get due to the input of y1 beta I, and a matrix, that is the refraction matrix, first refraction matrix Rm1. This one is the refraction matrix, which is the first refraction matrix. Next, here the translation from Q to S, that is the second translation from Q to S. Again we represent it in terms of matrix as y3 beta 2, here y3 angle beta 2, then that is y2 beta 1, y2 beta 1, that matrix T M2, second translation matrix T M2 is the translation matrix, that is the second translation matrix. Again at surface S refraction takes place, that is the second refraction at surface S. So here second refraction at S, second refraction at S, in matrix form we represent it y4 beta 0. So y4 beta 0 is equal to a matrix y3 beta 2, y3 beta 2, refraction matrix R M2, that is the second refraction matrix. This one is a refraction matrix, which is the second refraction matrix. Next, here translation occurred from S to Q, S to T. So translation, that is the second translation, sorry, that is the third translation from S to T. In matrix form we represent, that is y0 beta 0, y0 beta 0 due to the input of y4 beta 4 and a matrix, translation matrix M3, that is the third translation matrix TM3, that is the translation matrix From these four equations, let equation number 1 equation number 2, equation number 3, equation number 4 and equation number 5. So instead of equation number 5 we can replace in place of y4 beta 0 as this equation rm2 y3 beta 2, again the value of y3 beta 2 and again the value of y2 beta 1, like this. So from these 5 equations we get, from these equations we get, this is the output one. So y0 beta 0 is equal to, again putting its corresponding values, we have T m1 R m1 first translational matrix, first refraction matrix, T m2 R m2 T m3 yi beta I. Look here, that entire matrix is known as the system matrix. Here y naught beta naught is equal to Sm yi beta I. Here that Sm is known as the system matrix, that is the combination of translation matrix and refraction matrix. So we can write it y naught beta naught, y0 beta 0 is the output one and yi beta I, that is the input one. So output matrix, so we get here output matrix is equal to system matrix into what? Input matrix. That's the important point. Output matrix is the system matrix into input matrix. System matrix is the combination of translation matrix and refraction matrix. Now we understand the translation matrix and refraction matrix one by one. First one, for translation matrix, how to calculate translation matrix? Translation matrix, let me consider a lens here. Here is a point object. After refraction, let the image is formed here. So that point object is at a distance of, or at a height of y1 from this optical axis, and that image bb dash at a height of y2, and angle sustained here, let alpha 1, and angle sustained here, let alpha 2, and the distance between A and B, let D be the distance between A dash and B dash, and here the refractive index be same as the translation occurred in that of same medium. So the refractive index is same here. Having refractive index, let mu be the refractive index. Now mu alpha 1 is same as mu alpha 2. Therefore alpha 1 is same as alpha 2. Look here, in that of triangle, so equation number 1, again y2 is equal to y1 plus this section is equal to d times into tan of alpha 1. So d times tan of alpha 1. Since we consider for paraxial rays means the rays are very close to that of principal axis, so the angle subtension will be very, very small. So that tan alpha 1 is nearly equal to alpha 1, or y2 is equal to y1 plus d alpha 1, due to for paraxial rays tan alpha 1 is nearly equal to alpha 1. Angle subtension is very, very small. Let equation number 2. Now we represent these two equations in the form of matrix. Very simple thing, the matrix formulation we take. So by taking these two equations, here we consider let y2 and alpha 2 here, y2 alpha 2. So the combination looking here alpha 1, here the components of y1 at 0. Look here, that term is written as, so alpha 2 is written as 0 y1 plus 1 alpha 1. Therefore that and this can be written in terms of matrices. So y2 alpha 2, so the components of coefficients of y1 here will be 1, coefficient of alpha 1, that is d. Here coefficient of y1 0, coefficient of alpha 1 1, and y1 alpha 1. That one y2 alpha 2 is the output. This is the output matrix. y1 alpha 1, this is the input matrix, and that matrix is the translation matrix. That is the translation matrix. So the translation matrix is 1D01, that is a 2x2 matrix, as we studied here. The translation matrix will be a 2x2 matrix. So here output matrix is translation matrix into input matrix. So in this way translation matrix is calculated. Next, how to calculate refraction matrix. Refraction matrix. That matrix is important when we calculate system matrix for thick and thin lens. So please remember that particular equation here. Next, refraction matrix. Again we consider a convex refracting surface having refractive index here mu2, here refractive index let mu1, and a point object A. After refraction on that of surface, it goes like this. See, So the normal at the refracting surface that goes to that of center of that curvature. So the normal let the radius of curvature be r, that one is the normal. So that angle, the angle of incident, that angle, the angle of refraction r. Then the line parallel to that of principal axis, that line which is parallel to that of principal axis. So the angle created here, let alpha 1, here the angle alpha 1, that angle let alpha 2. So the remaining angle be phi and phi. So this angle will be phi and that angle will be phi, and the sum will be 90. Therefore we can use the Snell's law here. Using Snell's law, what we have? The refractive index and sine of angle. So refractive index be mu1, sine of angle, that is sine I, is equal to, again refractive index, sine of the angle, sine of angle r, sine of r be same. Since we consider the paraxial rays, as we taken, these rays are very close to that of principal axis. Due to that paraxial rays, sine I is nearly equal to I, sine r also nearly equal to r. Instead of sine I and sine r, we can substitute I and r. Therefore mu1 I is equal to mu2 r. Look a point here. Here I is the sum of alpha 1 and phi, alpha 1 plus phi, and r is the sum of alpha 2 and phi. Instead of I and r, we can put these values. So we have mu1 alpha 1 plus phi is equal to mu2 alpha 2 plus phi, or expanding that bracket, mu1 alpha 1 mu1 phi is equal to mu2 alpha 2 plus mu2 phi. We have mu2 alpha 2, so mu2 alpha 2 is equal to mu1 alpha 1 plus mu1 phi minus mu2 phi, or mu2 alpha 2 is equal to mu1 alpha 1 plus, taking phi as common, so mu1 minus mu2 of phi. Now mu2 divided on this side, so alpha 2 is equal to mu1 by mu2 to alpha 1 plus mu1 mu2 divided by mu2 phi. Look here, let that point, let point be here, is at a height, for this medium let y1, and for that medium let y2, y1 is equal to y2 here. And if we take this angle, that angle be alpha, so taking the tan of this angle, so tan phi is equal to y1 divided by r, y1 divided by r, or y2 divided by r, anything else. As we take the paraxial rays, so phi be very small, that is equal to phi nearly equal to y1 by r. So instead of phi, we can substitute y1 by r. Therefore alpha 2 is equal to mu1 by mu2 alpha 1 plus that is 1 by r mu1 mu2 divided by mu2 into y1. Again that is simplified as mu1 mu2 alpha 1 plus 1 by r. So mu1 by mu2 minus 1 of y1. Here is equation number 1. Again y1 is equal to y2, y1 is equal to y2, that be the equation number 2. Look here, when we write it in this way, so what we have here, that y2 is written as y1 as 0 alpha 1 plus 1 y1. So that equation can be compared with that equation, and we represent these two equations in the matrix form. So y2 alpha 2, so y2 alpha 2 is equal to a matrix. Here is that matrix be 1 0. Let first we take y1 term. So 1 0 1 0, then 1 by r mu1 mu2 minus 1, here mu1 by mu2 into y1 alpha 1. That is the output matrix, that is the input matrix. This is the output matrix, that is the input matrix. And that matrix is known as the refraction matrix, that is the refraction matrix. So in this way we calculate both translation matrix and refraction matrix. Now we calculate system matrix for thick lens and thin lens. Let we calculate system matrix for thick lens. How to calculate system matrix for thick lens? Look here, we consider a thick lens having thickness, let T be the thickness of thick lens, and the refractive index be mu2 be the refractive index of that thick lens. R1 be the radius of curvature of surface 1, and R2 is the radius of curvature of surface 2 of that thick lens. Let the refractive index of both sides of that lens be same. Refractive index of both sides of the lens is same. Let that be mu1, let be the mu1. Look here, that figure as you take here, if we consider a thick lens, so the refractive index of that of thick lens have mu2, and the medium, both sides of the medium be same, having the refractive index let mu1 and the radius of curvature of first surface let r1 and second surface let r2. So in that particular case, what happened? The ray passing through that of lens, if that one be the thick lens, the ray passing through the lens suffers two refractions and one translation. Translation through that of distance, where the thick lens is taken, the thickness, two refractions are the two surfaces and one translation through that of thickness. So here the system matrix of thick lens, system matrix for thick lens is calculated as one refraction, that is refraction matrix at second surface, translation matrix, one translation, the translation at the second surface, and refraction matrix at the first surface, first refraction. Now we calculate what be the values of Rm2, Tm2 and Rm1. So here, as you know, Rm1 the refraction matrix. So the refraction matrix is calculated. Here we calculate the refraction matrix like this. This one is the refraction matrix. So here the refraction matrix, that is 1, 0, 1 by r1 at the surface having the refractive index r1, that is mu1, mu2 minus 1, that is mu1 by mu2, and refraction matrix at the surface m2. Again for m2 the refractive index be changed, that is 1, radius of curvature 1 by r2, so it will be mu2 by mu1 minus 1, 0, that is mu2 by mu1, that matrix, the refraction matrix at surface m2, and the translation matrix Tm2 again, and the translation matrix Tm2, translation matrix, this is the expression for translation matrix. Instead of the distance we can say here be the thickness of that of lens. So the translation matrix is written as 1 T 0 1. Now putting all these values in that equation, putting these values, so we can find out the system matrix for thick lens. Putting these values, therefore putting these values we get system matrix for thick lens, system matrix for thick lens as S M thickness is equal to Rm1 1, 0, 1 by r1 mu1 by mu2 minus 1, mu1 by mu2 into Tm2, that is 1 T 0 1 into Rm2, that is 1 by r2 mu2 mu1 minus 1, 0 mu2 by mu1 this expression with the system matrix for thick lens. These are the values of refraction matrix and translation matrix. So here we calculate system matrix for thick lens. Now system matrix for thin lens. System matrix for thin lens. Look here, in case of thin lens, the thickness be 0. In case of thin lens, t tends to 0. Now in that of expression, we put t tends to 0. So what we have? S system matrix for thin lens. What we have? 1, 0, 1 by r1, mu1 by mu2 minus 1, mu1 by mu2, that matrix 1, 0, 0, 1. In place of t, just we substitute 0, then 1, 0, 1 by r2, mu2 by mu1 minus 1, mu2 by mu1. Now that is a 2 cross 2 matrix, so that matrix is multiplied with this matrix. 2 cross 2 matrix, 2 cross 2 matrix, 1, 0, that row to this column, that row to this column, the matrix multiplication. So 1, 0, 1 by r1, mu1 by mu2 minus 1, mu1 by mu2. Next, the matrix multiplication has that row to this column, so it will be 1, 0. Next, this row to that column is 1 by r1, mu look here. Here we take here as r2 and rm. If I change it that to this, okay, look here, that is 2, that is 2, 1, that is 2 by 1, again that is 1, that is 1 by 2, so 1, 2. Just alternate it. Same thing, 2, 2 by 1, 2 by 1, so that is 1, so 1 by 2, 1 by 2. Again, if the position will be changed, the result will be same, not confused. Just for our mathematical purpose, I just write it 2, 1, 2, 1. Okay, the result as mu1 by mu2 minus 1, mu1 by mu2. Now that is a 2 cross 2 matrix, that is a 2 cross 2 matrix. Then we can multiply to it row to column, row to column. Write it as 1 plus 0, 1 by r2, mu2 by mu1 minus 1 plus mu2 by mu1, 1 by r1, mu1 by mu2 minus 1. Next, 0 plus 0, mu2 by mu1 plus mu1 by mu2. The result will be 1. That value 1 by r2, mu2 by mu1 minus 1 plus 1 by r1, 1 minus mu2 by mu1, so 0, 1. Next, 1, that is 1 by R2 mu 2 by mu 1 minus 1. Here taking minus as common, so 1 by R1, here mu 2 by mu 1 minus 1, 0 1, that factor mu 2 by mu 1 minus 1, 1 by R2, 1 by R1 is known as the focal length. Here focal length of lens 1 by f is equal to mu 2 by mu 1 minus 1, 1 by R1 minus 1 by R2. So instead of that expression taking that term as common, so I write it directly 1 divided by, again look here, mu 2 by mu 1 minus 1, 1 by R1 minus 1 by R2. If I take here negative minus as common, so mu 2 by mu 1 minus 1, here 1 by R2 minus 1 by R1, that term is written as 1 by R2 minus 1 by R1. So that is 1, that is minus 1 by f, 0 1. So the system matrix for thin lens is equal to that one, 1 0 minus 1 by f, that is the focal length 1, and the system matrix for thick lens, all the parameters of the thick lens system matrix we calculated here. Not confused about the positions. If the positions are altered or not, the result will be same. Here I change it due to as I take that multiplication here. If you write the same thing, then you can choose that multiplication, that row to this column, then the result will be multiplied with that matrix, and finally the result will be same here. This is for system matrix for thin lens. So with the help of this video lecture, we understand matrix formulation of geometrical optics, the concept of system matrix as the combination of translation matrix. Here we find out the translation matrix and refraction matrix. Here we get the refraction matrix. These two matrices are used to calculate system matrix for thick lens. Consider a thick lens and system matrix at the combination of two refraction and one translation. Two refraction and one translation is calculated as we previously done. So that values are put here. Next, system matrix for thin lens. So in case of T, here I put 0. So solving this matrix multiplication, finally we get system matrix for thin lens. So with this useful and informative notes, let me wind up this session. Thank you.